describe? Is it? Okay, so I think I'm going to get started. Today we're going to talk about splay trees. This is going to be another example of amortized analysis, again, for a data structure. So splay trees. I think I asked this before, but I can't remember. How many people have seen splay trees before? Okay, some number. Okay, so splay trees. These are due to Slater and Tarjan. I think it's 85. Okay. And this problem, we have, so it's comparison-based data structure. And we support two operations. We support insert. Okay, so insert a key K, as well as find. So let's say, insert an item, which is a key together with a value, and find with a key returns the associated value. And you could also imagine delete. So it deletes item with key K, and this inserts a new item with key K and value V. Okay. Right, so if we were in a comparison-based data structure, how would we solve this problem? Yeah, this is a dictionary problem, so we can use hash tables. But here we're giving a comparison-based solution to the problem, which could also be used to solve things like predecessor, for example. Okay. And you might be wondering, in this class we see some pretty hefty data structures like fusion trees. Does anyone actually care in real life, right? So this data structure, for this data structure, there's this award called the Paris-Kanellakis Theory and Practice Award. And Splay trees won it in '99 for creating one of the most widely used data structures invented in the last 20 years. Okay, so the authors won it for the Splay tree. So apparently this is something that is not just in theory land. Okay, so so what are splay trees? So people have seen, I hope, some form of balanced binary search tree, like maybe a red-black tree, AVL tree, something like that. So a splay tree is, again, some binary search tree. So splay trees are binary search trees. Okay. But after every operation, we do some amount of rebalancing. So after each operation, the tree adjusts itself. No, so it's some rebalancing. Okay. Actually, I think the title of this paper is self-adjusting something or other. Okay. Okay, good. So what do I mean by adjusting itself? So this data structure operates in a model called the BST model. So BST stands for binary search tree. How does the BST model work? So at the beginning of each operation, we have a pointer to the root of the tree. Okay, and what can you do at each step? At each step, you can either walk to some child, okay, or walk to a child or to a parent, okay, or do a rotation. I'll say what that means. At each step, we can follow a child or parent pointer or do a rotation. Rotations are used to rebalance the data structure. Okay, so what's a rotation? So we have this big tree. So rotation. I'll just describe what it is by a picture. So somewhere in this tree we have a node X. We have a node Y, which is its parent. So this is going to be rotate X. X might have some subtrees hanging off it. Y also, this could be the empty tree. A, B, and C could be empty trees. But this is, in general what the picture looks like. And if we do a rotate on X, the rest of the tree stays looking how it was. But this picture turns into X now being the root. Y is now a right child of X. And then B and C now live here. And A lives here. Okay, so that's what I mean by rotation. And X could be the right child of Y, in which case there's a symmetric looking picture. Okay, so the point is that X now becomes the parent of its parent. Okay, and then these trees go wherever they need to go to keep the binary search tree ordering valid. Okay. So I'll get right to it and tell you how splay trees work. So to do a find, how do you implement find? Search for X as you would in a BST. I mean, a splay tree is a BST, right? So you start at the root and you just keep going down the correct child to get to where X is. Then, after reaching X, splay X. So splay is a subroutine that I will describe soon. Okay, it's going to do some number of rotations to bring X to the root of the tree. So whenever you search for X, after all the rebalancing is done, X is the new root. It's not just going to be rotate X over and over again until it's the root. It's going to be something just slightly more involved than that, but not much more. And insert X. So insert as in any BST. So you find where it should go and put it there. Then splay X. Okay. And delete there are several ways you can do delete. One way is splay X, then remove X from tree. Okay, well, when you splay a node and it's the root and now you remove it, if it had things in both its subtrees, now you have like 2 different trees. And you want to make sure that you have one tree at the end of the day, right? One binary search tree. So what do? If X had 2 children, splay the largest element in the left subtree and make it the new root. Okay, so what does that mean? Just to draw a little picture. So You have a tree. X was somewhere. You splayed X. Now X is the root. And then you deleted X. And then now you find the largest element in this tree. Let's colors. And you bring that to the top. And then now you add that, so it becomes a new root. Okay, so that's how you do deletes. Okay, so at the minimum, we know that with binary search trees you can get log n time per operation using, say, red-black trees, AVL trees. So splay trees, we'll show that you get that with splay trees as well. But one of the fascinating things about splay trees is that they have all these other properties. Okay, so for example, I think I mentioned this last time. They have the static optimality property. This was shown in the original paper by Slater and Tarjan. Let me just say Slater and Tarjan, 85. Okay. So for any sequence of operations and any fixed binary tree T, let's say the time to perform all ops with the splay tree is big O of the time to perform all operations with T. Okay, so if you knew the entire sequence of operations ahead of time, let me say, let's say any sequence of, that's what I want to say, of find operations. So let's say that the n items are fixed, okay? And you know what all the finds in the future are going to be. You know what they are and what the order is, okay? And now you want to build a binary tree, a binary search tree, which services that sequence of finds as fast as possible. So you can do this, I think I mentioned at the end of last class, with dynamic programming. You can find such a tree. If you're not familiar with that, I think it's in CLRS. It's definitely in the lecture notes from CS124 last semester. But splay trees don't know the future, right? I showed you exactly how find works. It doesn't know what the future operations are going to be, yet the time that a splay tree takes to perform all these operations is within a constant of the best tree, right? It's within a constant of any tree, in particular the best tree for that sequence. So that's static optimality. There are other properties that splay trees have. One other one is called the working set property. This is also in Slater and Tarjan. Okay. So I need to give you one piece of notation, one definition. Let Tj be the number of items accessed since the last time we saw the jth item in the sequence, of operations. So again, let's say we have a bunch of finds. Okay, so we have find on some xi1, xi2, xi3, xim. So we have m operations, a bunch of finds. And let's say here we have the item that we search for is 7. And 5 steps ago, we searched for 7 in the past. then what I'm saying is tj will be 5. Okay. How many items were there in between the last access to this item? So that implies that splay trees achieve O of m plus n log n plus the sum j from 1 to m of tj time, log of tj. Okay. So it's not just log in the number of nodes, it's log in how many nodes were there since the last access. And it's called the working set property because if there's a stretch of time where you keep searching for the same 10 nodes over and over again, then you're going to start spending constant time, log of 10. Okay, so like those 10 nodes will be your working set. There are a bunch of other properties it satisfies. I think I'll just name a couple more, and then I'll state a conjecture regarding splay trees, which hasn't been proven yet. Another one is the static finger property, also in the original paper. Okay. It says let f be any fixed item. Okay, and I said there are n items in this data structure. Let's just assume that the keys are actually 1, 2, 3 up to n. Okay, since it's a comparison-based data structure, all that matters is relative ordering. So let's just assume that they're all ordered like this. So I is actually the rank of the ith item, but just assume it's the ith item, the ith key. Let f be any fixed item. Then the amortized cost of find I in a splay tree is O of log f minus I plus 1. Let's say log f minus I. Okay. So this is true for all f. So you can pick f, for any given access sequence. The amortized cost per operation is this for a fixed f. So it's true in particular for the min over all f. Okay. That's the static finger property. People look puzzled by this property. No. So if you're spending a lot of time searching for keys that are near f, I mean, you can search for anything, but if most of your searches are near f, then you're servicing this access sequence cheaply. Yeah.
So what does that mean when I is f?
Yeah. So f minus I is 0. So okay. So plus 1. So I mean, this part is always going to be at least 0, but then there's a 1. So your time is always going to be at least constant, but in general, it's log the distance to f. Yeah, I didn't mean to put log of 0, I guess. Okay, so there's also the dynamic finger. This is actually not due to Slater and Tarjan. And let me see who this is due to. Cole is one of them. Cole, Mishra, Schmidt, and Siegel. So there are 2 papers, Cole, Mishra, Schmidt, and Siegel, as well as Cole by himself. They're both from SciComp 2000. What does this say? Suppose access sequence is, again, x1, x2, xm. Then amortized cost of the ith operation is big O of log of xi minus xi minus 1 plus 1. So it's the reason it's called dynamic finger is here your finger always stays on F and you're measuring distance to F. Here your finger always moves to the item you last searched for. Okay? And the proof is, I think, at least more than 100 pages. Okay, so yeah, we're not doing it in class. Don't worry about it. Yeah, so I don't know, this is very like, well, this paper is not by Tarjan, but I feel like this is very Tarjan style, that the data structures or the algorithms themselves are often very simple. I didn't define Splay yet. It's going to be something simple. But then the analysis is the thing that takes all the hard work, which is great for a programmer, right? If you actually want to implement a data structure, who cares how long the proof is? It only has to be proven once, whereas with the implementation, you might have to implement it in different languages or change the implementation a little to have some other property or something. You don't want to implement really complicated data structures that you then can't later debug, et cetera. Well, okay, so I guess it is nice to have short proofs too, because people can check it then, and also people can build on it. But yeah, it's anyway. So that's dynamic finger. I think I want to say there's also something called the unified bound, which tries to unify, I think, dynamic the finger property with the working set property, which says that so instead of paying log of, you basically pay log of the sum of these two things. So there's the unified. This was introduced by Iacono in 2001. We want the cost of operation J, the amortized cost, to be sort of the min over all I less than j of log of let's say xi minus xj plus, I guess, j minus I. Okay, so it's called a unified bound because it unifies the working set property and the finger property. So there should be some item beforehand which you are close to and didn't happen too far in the past. So it tries to unify those two things. Unfortunately, it's not known that splay trees achieve the unified property. Okay, it's not known that any BST satisfies the unified property, but Iacono then gives a data structure which does achieve the unified property, but it's not a binary search tree. Some other, it doesn't operate in the BST model. Okay, but it's an open problem. The closest thing is we have, I think, Derryberry and Slater, WADS 09, okay, services M operations in time O of M log n plus the unified bound. This is the unified bound on the sequence. So to really with some BST, not with splay trees, they give a different data structure which achieves this bound. So what you really want here is m, not m log n. But OK, that's what's the best that's known. And so I still haven't told you what Splay is, but before I tell you what Splay is, I will state the granddaddy of them all or something. So I defined for you what the BST model is, right? So at the beginning of every step, your finger's at the root. You can follow pointers. You can do a rotates. Okay, you can rotate the node you currently have your pointer set to. So then there's something called the dynamic optimality conjecture. This was I think in the original paper itself. And it's been open ever since, which I guess is almost 30 years now. So what does it say? OK, so with static optimality, I guess static optimality is right here. We just have, we're just comparing to a fixed tree. OK? Dynamic optimality lets the tree change. Okay, so the tree so there's a set of like BST algorithms, right? At every step you can choose, am I going to move this pointer? I'm going to move down or up? Am I going to rotate? So the dynamic optimality conjecture says that splay trees basically do the best that anything could do. Okay, so let opt be the, let's say, opt of sigma be the optimal cost of servicing access sequence sigma in the BST model. Okay, so pretend you know sigma. You know the entire sequence, okay? And given that entire sequence, you're going to spit out to me what you do at every step. So at every step, you're going to tell me either go up, go down to some child, or do a rotate, okay? But you need to make sure that you touch you touch all the nodes in this access sequence, okay? In the order in sigma. The conjecture is that for all sigma, the splay tree cost of serving sigma is big O of opt of sigma. So there's a fixed constant independent of n or m such that for all access sequences, servicing that access sequence with a splay tree is at most a constant factor larger than the true optimal way to do it. Okay. So are people happy with the difference between dynamic optimality and static optimality? Okay. Yeah. So, right. So the BST model says that you have one pointer that's always at a node somewhere, and at every step you're allowed to either follow one of the children pointers, go to a parent pointer, or do a rotate on the node you're currently pointing to. And every time there's an access request, you need to make sure that your finger moves to where that node is. Okay.
Is the rotation also specified to be exactly that?
So rotations are the picture I drew.
Exactly.
Yeah, that's a rotation. That's what rotation means. Okay. So let me write this like at most c times opt of sigma. So for some fixed constant c. So question for you. suppose that I didn't insist that this c were a constant. I allowed it to be a function of, let's say, n, the number of items. What's one small value of c that is already known? Huh? Wait, what'd you? Yeah, log n. Yes. Any balanced binary search tree will get you at most opt times log n. Why? Because for each operation, for each element in this access sequence, you need at least constant time just to touch that node. And a balanced BST is spending at most O of log n. So it's at most log n times opt. Okay. There was a data structure. So Tango trees. This is due to I think Domain, Harmon, Iacono, and Petroshku. This is in 2004. Achieve C being O of log n. Okay. So these are not splay trees. Actually, these trees are not dynamically optimal. Okay. They were purely designed to see how low can we make this C, right? Because we know that log n just follows from really old results in binary search trees. So can we get something closer to constant? So they showed that there is a BST model data structure that gets log n. And later there was also another paper by Wang, Derryberry, and Slater in SOTA 2006 that also got big O of log n, while simultaneously having log n worst case, or log n amortized time per operation and log squared n worst case. So this doesn't have any good guarantees on worst case or amortized bounds. At least not as good as the multi-splay trees by Wang and the others.
So now the optimality condition, the big O finds only universal constants.
Yeah, that's right. Yeah. So okay, so finally I should actually tell you what the data structure is by defining splay. Okay? So I said that the purpose of splay is to bring a node to the root. Okay. So just rotating x over and over again until it's the root is you can create examples where that's not good. So for example, suppose that you have a tree that looks like, so I mean this rotation is supposed to gradually keep the tree balanced somehow, right? If we want amortized log n per operation, that sort of means on average the tree looks balanced. So suppose that we just kept rotating things up to the root. So let's say we have something that looks like 6, 5, 4, 3, 2, 1. Let's say that it's completely out of balance. And let's suppose that our fake splay operation was just keep rotating till it's the root. So keep rotating 6. So suppose that we did a find on 6, and now we have to rotate it to be the root. Then the picture is going to look like 6 is up there, and then I think it's going to be 1 here, and then 2, 3, 4, 5. If I didn't mess up, that's, I believe, what it should look like. So in other words, the depth used to be n and it's still n. Okay, so that's not good. Okay, so how does splay work? So I'll just define it, and it'll look like magic. And with Fibonacci heaps, at least I could sort of say where they came from if you started off with binomial heaps. With splay trees, I've met both Slater and Tarjan. I've never actually asked either of them why they did this. But a friend of mine who went to CMU, where Slater is, he apparently asked Slater several times. And Slater apparently gives different answers depending on when you ask him. And one of the answers was just the math works. So, so yeah, it is somewhat magical, but it's a simple thing. It just seems to come out of nowhere. And even in hindsight, it's not obvious why it's so great. So how does Splay work? So this is not a good idea. So how does splaying work? So they're going to be so splay x repeatedly do the following to x. Okay, so there are going to be three cases. So okay, before I say the three cases, suppose that y is the parent of x and z is the parent of y. Okay. Now, there may be, so we're done when x is the root. So x definitely has at least a parent. It might not have a grandparent because maybe the parent of x is the root itself. Okay. So there are three cases. So case one, y is the root. And I'll say what to do in that case. Case two is that x is the left child of y, and y is the left child of z, or x is the right child of y, and y is the right child of z. So x and y these child pointers are both going in the same direction, left, left, or right, right. And then case three is everything else. So x is left of y, and y is right of z, or x is the right child of y, and y is the left child of z. So those are the three cases. And what we do in the three cases is going to be different. Yeah, okay, that's what I thought. So case one. So y is the root. We'll just do rotate x. And now x is the root. Case two. We have left, left, or right, right. We'll do rotate y, then rotate x. And then we have case three. We'll do rotate x, then rotate x. Okay. So that's Splay. Okay, so we'll keep looking at x. We're in one of the three cases. We'll do the corresponding thing. And then we'll iterate this until x is finally the root. So maybe I'll draw a picture. We already said what rotate looks like, so there's not really much to show you for case one. For case two is like, say, left, left. So pictures. Case two looks like z goes to y, goes to x. And then x has a and b down here, c, d. So when we rotate, let's say we rotate y, that's going to look like y, z, d, c, x AB. And then now we rotate x, and that's going to look like x, y, z. And then A, B, C, D. So that's case 2. So case 2 will bring us from this picture to this picture. Whereas case 1, or case 3, sorry, case 3, right, so this was, we went left and left. There's an analogous picture for going right and right. I'm not going to draw it. Case 3, things go in different directions. So we have z up here. We go left to y, then we go right to, z, to x. So here we have A, B, C, D. So I said the first thing we do is we rotate x. We rotate x twice. So the first rotate x looks like z x y is less than x, so here. And then this is A, B, C, D. And then we rotate x again. And then that brings it to look like this: x, z, y, d, c, a, b. Okay. And sort of, I mean, this is not going to be a proof of anything, but it's at least a hint that something is good. We could ask ourselves, what does doing a splay on the leaf of a path do? Right? So I drew a picture before that said if you just keep rotating x, it doesn't look that great. So at least, whatever we're doing now, hopefully it at least fixes that problem. So let's just look at splay on one of these things. So suppose I have 6, 5, 4, 3, 2, 1. And then I splay on 6. Actually, in my notes, I don't know why I did this to myself. I just made it one different. I don't want to have to think on the fly and draw a wrong picture. Okay, so what is there's stuff hanging off at the bottom here. I'm not going to label everything, otherwise this is. So if you splay on 6, what does that look like? I'll draw it for you. Wait a second. Can someone tell me something that's wrong with this picture? Yeah, so these are all negative numbers. Whoops. Now this picture is at least sensible. I don't want to keep writing negative numbers, but alas. Okay, so 6 minus 6 has to be on the top, we know. And then we have minus 1 hanging off and 0. Oh, really? Oh, you're right. So I really messed up myself. So this should really be minus 1 should be off to the right. And then now minus 2, minus 3, minus 4, minus 5. Okay. Good. So what this looks like There should be one thing left. And these trees are still around. Okay, so yeah, please, in the lecture notes, I guess, please don't have minus signs. Yeah, those, okay, so the main idea is if you do splay on a path, basically half the path gets put here, and then each one has a node hanging off. Okay, so the depth decreased by about a factor of 2. So that's at least promising. It's not a proof of anything, really, but so promising that we're heading in the right direction. So let's actually prove something. So claim the amortized cost of an operation is, what do we want it to be? Log n. So we're going to use the potential function method. Okay. So before, is that from outside? Okay. Oh yeah, it's someone in the hallway. Okay. So before, when we were dealing with Fibonacci heaps and binomial heaps, things were easy to picture in your head because we had this, adding money to this bank account and taking it out later when we needed to spend it. Now the potential function is going to look a little more complicated, and we're going to have to use one inequality at some point, okay, namely AMGM. Geometric mean is at most arithmetic mean. You'll see where that's going to come up. But okay, so the strategy is going to be the potential function method. Okay, so we're going to give every item x a weight wx. We're going to define s of x as being the sum over z in x's subtree of the weight of z. So this includes x itself. So the sum of all the weights in its subtree. And r of x is going to be log of s of x. Okay. And then now we can define our potential function. The potential at any given state is the sum I from 1 to n of r of I. Okay? It's the sum of all of these. I don't know what to call this. I think some people call this the rank of x. This is the sum of all the ranks in the data structure. Okay. So that seems like it's out of thin air. It sort of is. So yeah, I'm sorry. That's sometimes things are magical. What can you say? So so what we want to do now is bound. So first of all, let's look at find, right? So the cost of find is basically the cost of the splay operation, right? Because we walk down and then we splay back up. And the cost of splaying back up is the actual cost, not the amortized cost, the actual cost of splaying back up is proportional to the height of the tree. Or to the height, not the height of the tree, but the length of the path down to x. So we can charge going back down to x to the splay, which brings it back up. So the amortized cost of a find, for example, is just big O of the cost of splaying. So let's figure out what is the amortized cost of a splay operation. Okay. So question. So the amortized cost. So the cost of a find is big O of a find on x is big O of the cost, amortized cost, the cost to splay x. So what is the amortized cost of splay x? Okay, so let's figure this out. So remember how splay works. We just keep doing one of. You know what? I do not want to erase this. So I will erase this. Okay. So Splay has a number of like mini Splay operations inside where we're either in case 1, 2, or 3 over and over again, right? So let's figure out the amortized cost of, let's say, a case 2 operation. And then we can just sum up everything as we Splay all the way to the top. Okay? So I'm only going to do the amortized cost of Splay 2. Like, everything else is case 2, I mean. Everything else is kind of similar. So otherwise, you have to look at, OK, what if it were right, right? What if it were left, right, right, left? It's just pointless to do this in class. OK, so I'll just do one. So let's look at case 2 going left, left. So that picture up there. I mean, y is left zip, zip, z, and x is left of y. Now, remember, amortized cost, the definition we gave is the actual cost plus the difference in potential. OK? So the actual cost, we do 2 rotations. So it's a constant. Let's say a rotation costs 1, following a pointer costs 1. So this is, let's say, a cost of 2. You can put, I mean, whatever constant it actually is on your machine, put that there. You can make this proof work. OK, it's not a big deal. Now, how about this thing? This thing, we will show is at most 3 times r prime of x minus r of x minus 2. Now, what's r prime of x? This is the new rank of x after we do the 2 rotations. So I mean, here it has some rank r of x. And finally, after we do the 2 rotations, it has some new rank r prime of x. Okay, so notice this 2 is going to cancel that 2. And when we sum over all of the these case operations going to the root, it's going to telescope, and we're going to be left with r of the root minus r of x to begin with. Okay. Remember, it doesn't matter who the root is. R of the root is always the same because you sum over everyone in the whole tree. Right? So. Okay. In fact, amortized cost of cases 2 and 3 are both at most 3 r prime of x minus r of x. For case 1, it's at most 3 r prime of x minus r of x plus 1. Okay, so this is the thing I'm going to show. We'll show this for case 2. But just take my word that you also get the same thing for case 3, and you get an additive 1 for case 1. So that implies
Do you need to have this minus 2?
minus 2.
Yeah.
So the
If you didn't have, then
so the yeah, go ahead.
the actual cost won't cancel and you would telescope it.
Oh, yeah. I see what you mean.
Length of the path.
No, so the amortized cost is defined to be the sum, the actual cost plus the change in potential. So, right. So, yeah. So let's see. That implies that the amortized cost of Splay X is at most O of 1 plus, 1 plus 3 times r of the root minus r of x, which, if you remember, r of x is the log of the sum of weights in the subtree. That's going to be at most O of 1 plus log of w over s of x. W is the sum over all weights. Right? S of the root is just the sum of everything. Okay, so now let's actually show this for case 2. Okay, so change in potential, that's the thing we're trying to bound. So let's look at this picture. If you look at all the nodes in the trees A, B, C, and D, none of their f values actually changed. None of their r values actually changed. Right? Nothing, like the set of descendants in their subtrees all stayed the same. So the only people who did change are x, y, and z. Right? Their r's changed because the people in their subtrees changed. So case 2, the difference in potential is r prime of x plus r prime of y plus r prime of z minus r of x plus r of y plus r of z. Right? Okay, now r prime of x equals r of z. right? Because the set of items in its subtree, the set of items in X's subtree here is the same as the set of items in Z's subtree there. So let me write some facts as we observe them. So this is equal to, so what got canceled? R prime of X will cancel R of Z. So this is equal to R prime of Y plus R prime of Z minus R of X minus R of Y. This is because R prime of X is equal to, is this visible? I don't think this blue is very visible. R prime of X is equal to R of Z. What else do we know? We know that R prime of Y is less than or equal to R prime of X. Right? Let me make sure I'm not using bogus inequalities here. So we're also going to use the fact that, let's see. X. Yeah. How did I seem to have confused myself? So this is at most, I want to say. I know that R of Y is bigger than or equal to R of X. So R of Y is bigger than or equal to R of X. So this is at most R prime of Y plus R prime of Z minus 2R of X. And then I know R prime of Y is less than or equal to R prime of X. And then this is less than or equal to R prime of X plus R prime of Z minus 2R of X. This is because R prime of X is greater than or equal to R of Y. R prime of Y. Yeah? Okay. Yeah. So now let's do a little more. Now I want to bound this business here. So let's look at this thing R prime of X plus R prime of Z. Let's bound it. Let's divide by 2. Okay. What is this thing? This is log of S prime of X plus log of S prime of Z over 2, which is the same thing as log of the square root of S prime of X, S prime of Z. Right? And then now we use the fact that the geometric mean is at most the arithmetic mean. This is at most log of S prime of X plus S prime of Z over 2. Did I? Huh. Why am I feeling not so happy? This is not what I would. So let's actually, yeah, I know why. I actually want to bound this. Okay, so this is not exactly this, but we're going to see that this thing is going to pop out. Okay, what we actually want to do is we're going to bound R prime of Z. So this work that I'm doing here is to eventually bound R prime of Z. I'm sorry? Why can't we bound R prime of z with R prime of x? What do you mean? You mean right now?
No, I mean like x is on top of z, so r prime of x is bigger than r prime of z.
So at the end of the day, remember the bound that I want. I want everything in terms of x. Right. So yeah, I see. That actually seems to make a lot of sense. I'm sorry? So yeah, I think. Okay, so yeah, what you're saying. Okay, so yeah, I think okay, so I'll do it this way and show you. This won't matter that much for getting the log n, but when I want to show like one of the other properties, such as, for example, working set or static optimality, I'm going to fudge my definition of like this potential phi a little bit and allow phi to be negative. Okay, and then we'll go back and see what that means in terms of like bounding real cost in terms of amortized cost. But once I do that, I'm going to allow these like r primes to be negative numbers. So like I'm going to allow, yeah, so things that are above you in the tree could be even more negative potentially.
So, but then how can you replace y with x?
Oh, I see. Oh, yeah, that's a good. So yeah, this is a very good point. Now I'm.
So like changing phi is like potentially negative, right? So it seems like you can't just.
F prime of z is at most f prime of x. Yeah, actually what you're saying makes a lot of sense. So I don't know why I read this proof.
Is there any particular reason we need the 3
No, that's not important. But yeah, this makes sense. So the point you're saying is this thing here we can replace by, so this is r prime of x plus r prime of x minus 2r of x.
You don't have -2.
I need the minus 2. Yes. Whoa. Yes. Okay. Thank you. Okay. Now I know why I need to do this. Okay. I need to kill that 2 over there. Okay. Does that? Okay. Okay. So I completely forgot about that too. So let's go back to business. So I want to bound. Good. So I don't just want to bound. I don't just want to bound r prime of z by r prime of x and get 2. I don't just want to get big O of r prime of x minus r of x. I also want to get this minus 2 to kill that 2. Yeah, that was the key. Sorry about that. Okay, so let's go back there, and I want to bound r prime of z. So this is equal to that is equal to that. I applied AMGM. Okay, and now. So I actually, even with this, even what I said with negative numbers, I am going to maintain the property that as you go up in the tree, our ranks are only going to be non-decreasing. Okay. So now let's look at S of x plus S prime of z. S of x has all these nodes. S prime of z has all these nodes. Okay. So if you take the sum of them, you have everything except for y. Whereas everything is S prime of x. So this thing here is at most S prime of x. So this is at most log of S prime of x over 2, which equals r prime of x minus 1. And then now you multiply by 2, and you subtract off r of x. So now I can get rid of this picture finally. Are people happy with me? Are people happy with this inequality? Okay. So multiplying by 2 and bringing over the r of x, this all implies that r prime of z is at most 2r prime of x minus r of x minus 2. Now we plug that in for r prime of z there. We get 3r prime of x minus 3r of x minus 2. So this all implies that delta phi is at most 3 r prime of x minus r of x minus 2, which, as I said before, implies that the amortized cost of Splay in case 2, anyway, and it's also going to be true for case 3, is at most 3 times r prime of x minus r of x. Okay. Yeah. I mean, of just one. I mean, just doing. Yeah. Sorry. So amortized cost of case 2 is what I really meant to say. Okay. But if you did the same exact thing for case 3 or a similar thing, you would get the same bound. If you did it for case 1, you would get an extra +1 here. So you only pay that +1 once in the entire Splay, namely in the last step, potentially the last step. Yeah.
So if you have a +1, then why can't you just like double your potential function?
Sorry, say it again.
Why can't you just like double it? Oh wait. Oh, so delta v will not have any minus terms instead of the.
So I mean, at the end of the day, this telescopes all the way up to the root, and you pay r of the root minus r of x. So I don't know if maybe I misunderstood your question.
So I guess the +1 like comes from, is that because the actual cost will be 1, but the delta v won't have any minus terms?
Oh, when you're in case 1, where does the +1 come from? Well,
Because if delta v had a minus term, like multiply the
I see. If delta phi had a minus term, maybe I'm not sure what you mean by that.
No, like the -2.
Oh, I see. I see. Right. You're saying, right. So I guess so. The point is at the root you don't get to subtract stuff at the very last step. Yeah. Okay. I don't know if I'm answering your question, but okay. The cost of an operation is not negative, if that's what. If that's what. Oh yeah.
Why did you use arbitrary weights instead of just giving every weight 1? Is that for the negative?
Okay, so yeah, that's a good question, and it's going to bring me to now proving the actual claim, which is that. So once you do it for all the cases and do the telescoping thing I said above, what do we have? We have that. Okay, so we said that the amortized cost of Splay x is O of 1 plus log the sum of the weights over S of x. Okay. So to answer your question, why did we deal with all this like arbitrary weightings, right? It's because we want to prove different properties of Splay trees, for example, having the working set property or whatever. If we just want to prove an amortized bound of log n, okay, then how would you define the weights? Yeah, if you make all the weights 1, this implies amortized cost of Splay x is O of log n. Why? Make the weight of x1 for all x. Then the sum of all the weights is n, and then you're dividing by something which is at least 1. So you have log n here. Okay. But what if you want to prove these other amazing properties of Splay trees? So what about, so I'll just do 1 before the end of class. What about static optimality? How'd you define the weights there? So the items, let's say, are 1 up to n. Okay. Let's say some tree T puts item I at level L sub I. I should mention the way that I'm going to do the analysis now is a way that I saw done by David Epstein. So the way static optimality is originally phrased in the Slater-Tarjan paper is they show, how many people know what entropy is? Entropy, it's like Shannon entropy. Okay, so the thing about this static optimality, so the way I phrased static optimality at the beginning of the class is I said, for any tree T, for any fixed tree T, your Splay trees do as well as T does, okay, on the access sequence. But for a given access sequence, it's understood how well the optimal tree does. This is Huffman coding, okay? And what it does is it gets you a bound, a running time bound, which is proportional to the entropy of like if you look at the fraction of times you search for I as the probability of I, the Shannon entropy of that quantity is the bound that the optimal tree achieves. And Slater and Tarjan showed that Splay trees get the entropy bound. So yeah.
So does the sequence of accesses only include lookups, not delete and insert? Because if you
Right. So here, yeah, there's a fixed tree. So so I'm assuming, yeah, you have the set of n items given to you. And like the items are one, there are no insertions. There's just like finds over and over again. Okay. So Slater and Tarjan actually show that Splay trees achieve the entropy bound, but I don't want to have to define entropy and then show you that proof. I think it's more natural to just say, look, for any tree T, Splay trees do at least as good as T. Okay. And that was, so the proof I'm going to show you, not avoiding mentioning entropy, is a proof I saw by David Epstein. I think he just put it in his live journal at some point. I don't think it was even written in a paper anywhere. Okay, so the weight. And also, I'm not going to prove exact. You'll see what we prove. Okay, I'm not going to prove the strongest thing possible, but just to give you an idea of the flexibility of these weights. I'm going to define the weight of I as being 1 over 3 to the Li. Okay? So before I analyze Splay trees, say I is accessed, say find I is called ni times, or mi times. What's the cost of serving this access sequence using the fixed tree T? I mean, what's the time to do a find on I? Li, right? So this implies that cost with T is O of m plus the sum I from 1 to n mi li. Right? So that's the bound we want to say splay trees also achieve. So we'll show splay trees get O of m plus n squared plus the sum over I from 1 to n mi li. So as long as the sequence of operations is long enough, so no matter what initial configuration your splay tree was in. So your splay tree in the beginning is an arbitrary binary search tree on these items. No matter how you started off, after m operations, this is what the running time will be. So as long as the number of operations is big enough, it'll start like behaving as the optimal tree. Okay? So with a very slight change of this weight, it's possible to make this n squared be n log n. And in the actual Slater-Tarjan paper, where they just deal directly with entropy, this term disappears altogether, and they really show that it's up to a constant what it should be. Okay, but just to give you an idea, I just wanted to show you something more intuitive. Okay, so good. So remember that amortized time. Well, the amortized time for an operation is the actual time plus the difference in potential. So the amortized time of everything, of the whole sequence, is the actual time plus the final potential minus the initial potential. Remember, we're not starting with the empty tree, right? The tree started in some configuration, and then we kept running finds according to this access sequence. So this implies that the actual time is equal to the amortized time plus phi initial minus phi final. Okay. Now, I just want to say that this thing is bounded by n squared. And then this is going to be bounded by m plus this thing. So why is this bounded by n squared? I'm just going to say something very silly. If you look at any node and ask what its rank is, the worst case is that the rank is, well, this optimal tree T could be a path for all I know, right? In which case, some node can have depth n, and then log of 1 over 3 to the li is like basically minus n. Okay. So log of a weight in the worst case is minus n for a node. And in the best case, the depth could be at the root. And then this will give you, log of 1 will be 0 or something. So contributions of nodes are anywhere from minus n to 0. So for the whole tree, it goes anywhere from minus n squared to 0. So the potential is a number between 0 and minus n squared. So it definitely can't change by more than n squared. So this is at most n squared. You can do better, I mentioned, but then the proof just becomes very slightly more complicated, not much. How about the amortized time? Well, let's look at the amortized time of searching for I. Amortized time of find I is equal to, well, I erased the theorem, but it's log the sum of the weights. Well, it's the sum of the weights over s of x, s of I, plus 1.
It's up there.
Oh, it is up there. OK, good. Thank you. It is up there. And in the last 30 seconds, what's the sum of the weights? So weights are 1 over 3 to the li. How many different nodes can have a weight of 1 over 3 to the li? 2 to the Li, right? Weight is sum over Li, 1 over 3 to the Li times number L, number of nodes. Yeah.
Are you guys finishing up?
Yeah, like in 30 seconds.
Okay, great.
At height L. But this is at most 2 to the L. So this is at most sum over L 2/3 to the L, which converges. It's a constant. So you get basically log of 1 over 3 to the L. So this thing is going to be O of 1 plus Li, which is exactly what we wanted. Okay, so sorry I did a little rush at the very end, but this is just one property, the static optimality, but there are lots of properties, and you can prove many of them by just choosing your weight function appropriately. Yeah?
You know, these can be used to design compression schemes.
Compression schemes?
Because it seems very closely related to that.
Yeah, I mean, so the reason that the static optimal bound is entropy is related exactly to compression.
But here it's even better because it could be for that. You don't need to go before
Right.
and stuff like that.
Right.
So that could be like even like adaptive.
Yeah, I guess, I mean, you can say that, but I think I see maybe what you're saying, but I haven't really thought about like a coding application where you would want to use splay trees to change your encoding. Yeah, I don't know.
They're not physical order.
Oh, yeah, problem sets up front.